Well, good morning. It is Friday, November the 20th, the last day before Thanksgiving break. And for that, we are very thankful. 1 week from today, I'll be getting married.
Congratulations.
Let's just hope I do a better job on the second go around than I did on the first. Okay. Well, it is what it is, right? If the first one went well, I wouldn't be going for the second one. All right. Oh, you gotta laugh about it so you don't cry. Here we go. So, T1 and T2. Kinetic energy versus molecular speed. Really, the speed is, the kinetic energy is directly proportional to the speed, okay? But sometimes they use different labels for the x-axis. I'll get it out there, okay? So, who from yesterday can remember how do we measure the total number of molecules on this graph?
Area under the curve.
The area under the curve. And again, if I had drawn this to scale, the area under the purple curve is going to be the same as the area under the blue curve. I think it's a little bit greater based upon the way I drew it, but it's supposed to be about the same. But the whole point is that the range of the purple one extends. You have more faster ones. Therefore, the height has to be lower to accommodate the greater range. Because we're still dealing with the number of molecules. In other words, the speeds are getting more spread out. The faster, well, so which one is the higher temperature? T2 is going to be your higher temperature because this is going to be your average kinetic energy. The majority of the molecules have this much kinetic energy. Whereas here, the majority of the molecules have this much kinetic energy. Temperature is a measure of the average kinetic energy. So, if we have hydrogen and nitrogen, which one is M1, which one is going to be M2?
M1 is going to be nitrogen, and M2 is going to be hydrogen.
Okay, that is absolutely correct. And how did you get that? Why did you want to say that?
Because nitrogen is larger and will move slower than hydrogen.
Okay, that's exactly right. These are at the same temperature. Now that's the two things. That's the most important thing we have to say. Clarify. We assume they're at the same temperature, which means their average kinetic energy is going to be the same. So the kinetic energy of 1 is going to equal the kinetic energy of 2, which means that 1/2 mv squared is going to equal 1/2 m2v2 squared. Right? Now obviously the 1/2 is going to cancel out. But as this mass goes up, if this mass is greater than that mass, in order for the two to be equal, this velocity has to be less than that velocity. Right? So the whole point is that same temperature equals same average kinetic energy. So, two ways again we ask the question, and this is an important graph, and we're going to use this over and over again the rest of the year. Same temperature, same kinetic energy, but they have the same kinetic energy, but they don't have the same speed. The one with the greater mass is going to have a lesser speed. And I would say it this way. If you have a big mass, you ain't going fast. Okay? If you have a big mass, you ain't going fast. I'm slow. Okay? The thing is when I was small and skinny, I was still slow, but nothing's really changed that much. Okay. So that's just kind of the kinetic molecular theory in graph form. I just want to make sure that we're totally comfortable understanding this graph. Okay? It's all the higher temperature or the lighter molecule is always a lower hill, more spread out. Okay. Let's just talk about one or two more laws, and then we'll just do some practice problems and call it a day.
never won this, okay? Yes. Nothing's lasting.
Oh, okay.
Dalton's law of partial pressure. This one takes a while just to write, but it's pretty simple to actually comprehend. You're looking really cool there, Rick.
Thank you.
You're looking fly, I should say.
There we go.
Looking fly. Okay. In this room right now, really we have two gases, nitrogen and oxygen. Again, 78%. In the room, we have 78% nitrogen, approximately 21% oxygen, and what's number 3? Argon. There's 1% left. 0.93% of that is argon. That leaves how much? 0.07, right? Approximately, and this is, varies, is CO2. And then the rest is just trace gases. You have some of the noble gases present. So there's a little bit of xenon and krypton in the air. They were very difficult to find because there's such small quantities in the atmosphere. Okay, you got water vapor, you got pollution, you got all the other stuff that's in the atmosphere making up the other 0.03%. Okay? So, what causes pressure?
Collisions of molecules against the container wall.
Collisions of molecules. So right now, which molecules do you think are colliding with you the most?
Nitrogen.
Nitrogen. What percent of the 1 atmosphere of pressure do you think that the nitrogen molecules are exerting on you? 78%. Okay, because 78% of the collisions are going to be from nitrogen molecules. So it's just going to be based upon, the partial pressure is and this word messed me up for a long time in college because nobody ever really explained it to me. The partial pressure is just the part of the total pressure that each individual gas exerts. And again, I said this yesterday. The nitrogen is going to be colliding with us whether the oxygen's here or not. The oxygen's acting like whether the nitrogen's here or not. So this is just the part of the total pressure. Of the 1 atmosphere, the part of the pressure that's due to nitrogen is going to be 0.78 atmospheres. The part of the total 1 atmosphere pressure that is due to oxygen is going to be 0.21 atmospheres. Okay, so the partial pressure. So Dalton's law of partial pressure simply says, in a mixture of gases, the total pressure is equal to the sum of all of the partial pressures of the gases in the mixture. That's squeaking bothering anybody other than me?
No.
All right, in a nutshell, in a mathematical, we can say that in a mixture of 3 gases, A, B, and C, the total pressure is going to be the partial pressure of A plus the partial pressure of B plus the partial pressure of C. Now, a variation of that is what we refer to as Rahu's law. Rahu. that says the partial pressure of A is equal to the mole fraction of A times the total pressure. This is really what we just did right here when we figured out what's the partial pressure of the nitrogen. We took the mole fraction, the percentage of the moles, times the total pressure, 1 atmosphere, to say that 0.78 atmospheres is nitrogen. That's Rahu's law. Now, mole fraction, X of A is, what do you think mole fraction would be? What do you think this ratio is going to be to get this?
Moles of A over moles A, B, and C.
Moles of A, that's exactly right, over total moles. Okay? In our nitrogen example, that would be 78 over 100. We're assuming we have 100 molecules, 78 out of every 100. So the mole fraction is 0.78 times the 1 atmosphere gives me the partial pressure of the nitrogen. Okay? So mole fraction, and I don't know why they use X, it's just always, mole fraction is always X. So, I forgot to define that. Okay, and I'm just going to define 2 other words for you, and then we're going to do some practice problems. Okay? What is diffusion?
Spreading.
A gas spreading out area.
Okay, a gas just naturally spreading out. Now, it doesn't have to be a gas. You can put food coloring into water, and that food coloring is just naturally, slowly going to spread out and get a homogeneous mixture in the beaker, right? Why does that happen?
It wants to move from higher concentration to lower concentration.
But what's causing it to move? Why isn't that just sitting there?
Other forces acting upon.
That's true, but what are those other forces? That's what I'm trying to get to. So what was the second step, the second postulate of the kinetic molecular theory? Yeah, I put on the board yesterday. Continuous, rapid, random motions, right? So what causes the gases to diffuse?
Bumping against each other.
They're just in motion, they're just bumping into one another, they're just spreading out, they're moving, right? So which ones are going to be moving faster, the light ones or the small ones? The light ones. So if you have 2 gases that, you have 2 bottles of perfume or 2 bottles of different substances, one is a very big, heavy gas, the other one's a real light, small gas, okay? Which one's going to spread out faster? The light one, okay? If you have a big mass, you ain't going fast. So diffusion is just the natural spreading out of a gas, the natural spreading out of one substance through another. We're going to be talking about gases here, but it's the natural spreading out of one substance through another due to the continuous rapid random motion of the molecules. But it's the smaller one's going to go faster. And then there's another term that's related to diffusion called effusion. Effusion. What's that? You two had me last year, so we defined this term last year. Effusion.
Isn't it like the ability for it to go through like small?
That's right. The effusion is the escape of a gas through a small opening. I'm surprised that there's this much air in this balloon still. How does the air get out? There's little tiny pores in the latex, right? It seems like it's solid, but it's actually got little tiny pores. So if this was helium in here, it for sure would have been flat, because the helium can escape out of the pore. On the other hand, so you have to have the mylar balloons that don't have the pores for the helium balloons so that it doesn't leak out. Again, let's think logically. You have a little tiny hole. Is the small molecule or the big molecule going to get through that little tiny hole easier? The little small one, okay? I always envision, you know, I don't know, the goofy movies where they have the dog door and the big guy's trying to get through the little doggy door and they get stuck or trying to crawl through a window and it's too small, you know. If you're going through a tiny opening, the smaller it is, the faster it's gonna go through. It follows the exact same law as diffusion. The bigger the mass, the slower the rate of diffusion, the slower the rate of effusion. Now, you don't have to do anything math with this, but let me just show you the math. It's called Graham's Law. Hey, I can still see me. Graham's Law of Diffusion. Do I need to define diffusion, or are we good? You good with just diffusion and effusion? So make sure we just know. Diffusion is the natural spreading of one substance through another. Effusion is the escape of the gas through a small opening. All right, so you have two gases with mass 1 and mass 2. Okay? So in other words, two different gases, different masses, at the same temperature. So what do we say about kinetic energy?
The same.
So kinetic energy of gas 1 is going to equal kinetic energy of gas 2. So just like we did right over there, 1/2 m1 v1 squared is going to equal 1/2 m2 v2 squared. The 1/2s are going to cancel out. Bring the masses to the same side and the velocities to the same side. m1 over m2 is equal to v2 squared over v1 squared. The velocity is the rate at which they're going to be spreading out. So how fast are they going? So take the square root of both sides, and we end up getting the square root of m1 over m2 is equal to v2 over v1. Now, what do you think we use to measure the mass of a particular gas? Well, no, we use grams, but what do we call the mass? What general? Let me just say, most of the time we use molar mass here. Okay, so we could really re-say that this is the square root of the molar mass of 1 over the molar mass of 2 is equal to the velocity of 2 over the velocity or the rate of diffusion. Okay, this is really Graham's law right here. Now, you used to have to be able to do math with this, but the whole thing is the rate of diffusion is going to be inversely proportional to the square root of the molar mass. So if I'm going to compare, if I want to compare, I'm just going to go up here, compare CH4 with H2. First off, which one's going to be diffusing faster? H2. We can use Graham's law to figure out how much faster. Because we can say molar mass, I always like to do the heavier over the lighter. So I'm going to say 16 over 2. Actually, let's do the math a little bit easier. I'm sorry, let's change that to helium and make that 4. The square root of it is going to equal the velocity 2 over velocity 1. So 16 divided by 4 equals 4. Take the square root of it, it's 2. So 2 is equal to the rate. So this 16 is 1. This is 2. Okay? So the rate of 2 is going to be twice that of 1. So even though it's 4 times heavier, it's only 2 times slower. What I want you to take out of this is when gas is spread out, it's inversely proportional to the square root of the molar mass. Okay? All right. Believe it or not, other than doing stoichiometry problems now with the ideal gas law and plugging into these formulas, there's really, that's all the theory there is for this whole chapter. Okay? So we're just gonna try to remember some of it over the week. We're gonna have some practice problems to do with this, but let's just start. You have the books there still in front of you. So let's start off with number 9 on page 433. Number 9. Do we have answers? All right, so when we consider the following graph, if curves A and B refer to two different gases. So we have helium and oxygen. Now it's going to be important here, at the same temperature. Okay? So at the same temperature. That means what about their kinetic energies? They're the same. But which one is going to be A and which one is going to be B and why?
Helium's gonna be B.
Okay? Because
It's lighter.
it's lighter, therefore it is faster. Its average molecular speed is going to be greater. So again, when I look at this beaker of water right here, it's at a certain temperature, but not all the molecules inside are going the same speed. They're constantly bumping into one another. So think about pool balls. When the cue ball hits that ball, the other ball speeds up, the cue ball slows down. Then it gets hit and it speeds up and the other one slows down. So there's a constant transfer of energy. Now, what is true then, those of you in physics or whatever, if we're at the keeping a constant temperature but they're constantly colliding, what can we say about their collisions? Elastic, what does that mean?
They're perfectly aligned.
What does that mean? That's exactly right.
I mean, there's no energy loss upon collision.
Okay, there's no energy loss when they collide. Okay? There's no friction. Because they don't really collide, the electron clouds get close to one another and they repel and they just bounce off. So there's no loss of energy. That's why an aerosol can stays pressurized, as long as the temperature stays the same, because they don't lose energy bumping into one another. If it were inelastic collisions, little by little the heat would be dissipated, the molecules would be slowing down, the pressure would be going down, down, down. But
kind of like slide off of each other because they get close and
then they would just repel, yeah. Okay? But they're still affecting each other's speed. Okay? So, helium is smaller and lighter, moving faster than the oxygen. So on B, if A and B refer to the same gas at two different temperatures, so now we're at the same gas, which one's the higher temperature? B. Heat them up, speed them up. And then finally C, for each curve, which speed is highest? The most probable speed, the root mean square speed, or the average speed? I'm not even going to go there on that one, okay? Those are just different ways of calculating the speed. There's equations given, but you are not required to know how to do those equations, so I'm not going to spend the time to go through each of those. Root mean squared, anyway, I'm not going to go there. So we'll just skip C. All right. Turn the page. Now we're going to go through and just do a set 40, 42, and 43. 40, 42, and 43.
9 on page.
Okay. 40. Ultra
those three, then we'll go over those.
Certain they can. Okay, so PV equals nRT. Yeah, so we're looking for P. We have it all. Should we put it in liters? Look at P1, V1, for higher volume and lower function.
Yeah, yeah,
Because they're inversely proportional. Three more sample of that.
Okay, so there is the solution to number 40. You want to compare yours to number 40. And does anybody have any questions on this one? Again, on C, you're never gonna have to do this conversion. Okay, Fahrenheit will just never be used. You definitely do need to know Celsius. Now, they're using 273.15. We can use 273. We don't need to go to the 2 decimal place. Okay, because notice they just rounded here, 328 anyway. Does anybody have any question on that one? Does anybody need to keep seeing it? Can I go to the next one? Anyone? Okay, so 42 and 43. Notice it's just a rearrangement of the ideal gas law. So in 42, the tricky part is knowing that you're calculating the part that remains. And then you just subtract that from how much you started with. That's how much got you used. We'll go to the 42 and 43. Questions, anyone? Let's look at this second part of 43, the other parts of 43. That's 43, B, C, and D. y'all good with those? Any questions on these? You guys, apparently you know how to do all these, there's no questions, we got them all right? All right, that's good. All right, so let's take it up a notch. I want to work a problem like this with you. So then, when you get to the practice AP questions, all right. It says a 7.25 gram mixture of ammonium carbonate and potassium chloride is in a 5-liter container. So the 7.25 grams is a mixture, combination of those two chemicals. It's not all of one or the other. The mixture is heated until all the ammonium carbonate is decomposed. You assume nothing happens to the KCl, that it's just there. It's an inert ingredient, it's just there. So since they're only given, whenever there's a mixture and you're trying to separate the mixtures, one of the components is going to react, the other one's just going to be there, so you ignore it. It's just adding the mass. When the reaction is complete and cooled to 25, the total pressure, and that's going to be our key thing right here, this one I want to kind of show you. The total pressure in the flask is 1.07 atmospheres. What is the percentage of ammonium carbonate in the original mixture? Several things have to happen here. Okay? First off, ton of numbers, equations, words, very overwhelming problem. What's the question asked? Percent NH4 to CO3, right? What's that going to equal? How are we going to calculate this? What do we need to know? Not moles, this is mass percent. Mass of NH4 to CO3 divided by the total mass. But do we know that total mass? That's the 7.25 grams, right? So and then it's going to be times 100 to put it in percent. So what's the only thing we really have to find? The mass of this right here. How much of this reacted? That's really my ultimate question. Now it's very, very, very important that you kind of go through that process, because if you don't know what you're looking for, you're probably never going to find it. What's the question asked? What's the equation for that? What do I know about what the question is asking? And then isolate the one thing that I need to find. So I really now know I need to find this. So now I go back, well, what else do I know? I know that I have a 5-liter container, so the volume is equal to 5 liters. I know it's heated until it's all decomposed. The reaction is completed and cooled to 25 degrees Celsius, which we know to be 298 K. The total pressure is equal to 1.07 atmospheres. Now, what are the only gases? What's making up that total pressure? This is where we have the total pressure here. What's making that up? Think of Dalton's law of partial pressure.
All the partial pressures together.
Okay, so what gases are present?
Carbon dioxide.
When the reaction is completed, first off, this is a solid. It doesn't say that, but that's a solid. What gases are present? NH3. So it's the pressure of the NH3 plus
CO2.
the pressure of the CO2. Anything else? Water vapor. What's it say here? The vapor pressure of water. Even though this is a liquid, a little bit of it's going to evaporate. And you're going to be always given the vapor pressure. It depends upon what temperature it is. There's usually a table or something, you look it up, or in a problem, you're gonna be it will be given to you. So I know that I have the pressure of the H2O, but I know that one. That one is this. Right? Now, here's your trick. What's the relationship between the pressures of these two?
2 to 1.
How do I know it's 2 to 1?
NHs.
2 NH3s for every 1 CO2 are going to be produced, and pressure is directly proportional to moles. More molecules, greater pressure, right? We've talked about that a lot. So since it's going to be a 2 to 1 ratio, I can say that 1.07 atmospheres is equal to 2x plus x plus, now I'm in atmospheres here, so I really need to get this into atmospheres. How do I convert millimeters of mercury to atmospheres? Divide by 760. So it's 23.8 divided by 760 is the pressure of the water. So then you just find what that is, subtract it from here, divide by 3, and you get the value of x, which is this pressure right here. So can somebody do that? So 1.07 to minus parentheses 23.8 divided by 760 equals, then divide by 3.
I got 0.346.
0.346. And that's going to be atmospheres. Okay? So that's the pressure of the CO2. What am I ultimately looking for? So I know now that the volume here is going to be 5 liters. The temperature is 298 K. Now I know that the pressure of this is 0.346 atmospheres. How can I use that to find this?
Get grams of CO2.
Get grams of CO2. How do I get grams of CO2?
No, you get moles of CO2.
Okay, you can get moles first and then use,
Mole ratio.
well, we're getting to that, but before we do mole ratio, how do I get grams? Well, I guess we can just stick with moles, okay, because we can go moles to moles, because if we go grams, we have to go right back to moles. So how do I get moles? And I've turned this a little bit this way, please. Moles of CO2, what's that going to equal? What do we got? What equation are we going to use? We're going to use PV equals nRT, right? And so it's going to be PV over RT. So it's going to be the pressure, 0.346, times 5 liters, divided by 0.0821, times 298. So moles of CO2 0.0700 moles of CO2. So how do I use that then? I heard somebody mumble something. And what's the mole ratio between the CO2 and what I'm looking for? 1 to 1. So it's going to be this many moles times 1 mole NH4, 2 CO3 for every 1 mole of CO2. Then what do I do? I need grams, right? I need the mass, so I need grams. So how do I go from moles to grams? No, molar mass. So it's going to be 18, NH4 is going to be 14 and 4 is 18 times 2 is 36, plus 12 is 48, plus 48 is 96 grams per mole. So, whoop, no, we're getting grams, so that's gonna give me grams of ammonium carbonate. Is equal to how many? 6.79 grams. Some cat getting tortured out there, what? I don't have any, but I do this some, but, I was thinking a cat getting tortured out there, so.
Why did you just
Really?
kick off the
I
card?
think you could use more of that.
Oh, really?
You were up to this card.
All right, are we done yet?
Push it.
No, we're not done yet. So now, what do we do with this? This goes back, this is what we're originally looking for, that's this one. So, our percent NH4 to CO3 is going to equal 6.79 grams divided by, what was it, 7.25 grams times 100. 93.7%. So in our mixture, 93.7% was the ammonium carbonate. Now, this was a good problem. A lot of levels. Okay? Retroanalysis. Start with the question. Work your way backwards to know where to start. First thing we had to do is figure out what am I really looking for? Mass of ammonium carbonate. What am I given? I'm given these things. When you have total pressure, this is the trick. When you have the total pressure, you have to use Dalton's law and figure out all what gases are there and know that the gas pressures are going to be the same ratio as their moles. Okay? And if they're under the same conditions of temperature and pressure, the volumes are going to be the same too. But since we're getting twice of this versus this way, if we were collecting in a balloon, this balloon would be twice as big as that balloon. Okay? Or if we're in a sealed container like this one, the pressure's just double. So if it can expand, the volume would be double. If it's in a rigid container, the pressure doubles. Okay? So it all depends whether it's a flexible container like a balloon, or is it a rigid container, or whether the volume's going to change or the pressure's going to change. Does that make sense? All right. So then we just use the ideal gas law to calculate how many moles of the gas, and then just do normal stoichiometry to get to the grams. Good problem. All right, we got 18 minutes left, and you can use that to work on e-learning problems or study for a test in another class today.
Yes.